Yeah, yeah, sure.
Okay, hello back. I hope everyone is quite strengthened after lunch and not in a food coma. I'm Nico Jansen from RWTH, and I'm leading you through the third session of today. And we start with Lars Hummelgren from KTH in Sweden. You do quite a lot of work. It's not the first talk from you or from your university.
No, no.
And yeah, you start with Trellis, a domain-specific language for hidden Markov models with sparse transitions.
Thank you. So, does this work? Yeah. So, thank you. Thank you for the introduction. I will start this talk by giving an outline of what I plan to talk about today. So I will start off with an introduction where I sort of give you an idea of why this is useful and what exactly we're doing that others have not done before. Then I'll talk about hidden Markov models and give you an idea of why they're useful and sort of why sparsity is relevant here. Then we will look at the Trellis language, so how we design the language to make use of the sparsity. And then we look at the compiler side of things and how we actually generate efficient GPU code from this. Then we will look at some execution time results, and finally I'll give some concluding words. So let's start with the introduction. So hidden Markov models, or HMMs as I'll refer to them in the coming parts of the talk, are useful in many different research fields. For instance, they're used in bioinformatics, signal processing, and different kinds of pattern recognition. For instance, you can use them to align different nucleotide sequences to find similarities between different species. And the problem that we are interested in this work is specifically about sparse HMMs, and I'll get back to what I mean by that. But in these kinds of problems, it's interesting to consider those where we have many states, because that's when sparsity really becomes relevant. And in those cases, as it turns out by how the HMM algorithms work, we have lots of potential parallelism, because we have many things we can do in parallel for each state. And this is very well suited for a GPU, so we want to make use of GPUs here. But of course, implementing it on a GPU is very tricky and error-prone. And also, if we implement it for a particular model, then we have to specialize it for the sparsity of that model to make it really efficient. But then if we want to update the model later on, that's going to be really tricky. So we want to separate the model from the implementation. We want to have preferably a compiler that can do all the implementation work for us, just from a high-level specification of the HMM. So if we look at what others have done, of course, others have done work related to this. So here we show 5 different works that do similar things. So these are languages and libraries where you can describe HMMs on a high level, and where you then can sort of get the algorithm implementations for free. So you don't have to think about the implementation, but you only reason about the HMM. There are, however, a few problems with these. The first is that all of them, except for Palmkvist at the bottom, only run on CPU. so we can't really make use of the parallelism when we scale up the number of states. The second problem is that all of them are focused on dense HMMs, so in the sense that they don't really make use of the sparsity available in models, and there's no way to express it. They don't really optimize for those cases. So we lose the potential of making use of that. So in our work, we try to solve these problems. We have three main contributions in this work. The first is the design of a Trellis language where we can express the sparsity. And then we implement a compiler on top of this, which can generate efficient code from these sparse specifications. And finally, a key part of the sparsity, the compiler, is the predecessor computation, where we use the sparsity to produce efficient code in the end. So let's talk about hidden Markov models. So now I'm going to go through a concrete example, and then we're going to see why they're useful and also why sparsity is interesting. So in this example, we have two people, Alice and Bob. Alice and Bob live in different cities, as you can see. So each day they have a remote meeting with each other, and Alice has noticed that Bob's mood during these meetings varies a lot from day to day. So some days he's happy, others he's grumpy. And by looking at old weather forecasts, Alice determined that his mood is actually dependent on the weather. So he's more likely to be happy on a day when it's sunny. And this can be encoded as a hidden Markov model because Alice cannot directly see the weather in Bob's city because they live in different cities, right? So in a hidden Markov model, we have a hidden state. So in this case, it's the weather because Alice cannot observe the weather directly. And it's either sunny or rainy for this model. Then we have some output, which is something that we can observe. And for this model, that is Bob's mood. And Bob can either be happy or grumpy and nothing in between because he's a simple man. Then we have three probabilities. We have an initial probability, which specifies how likely we are to start in either of the hidden states. And for this case, we just say it's 50-50 sunny or rainy. We don't really know on the first day. Then we have an output probability, which specifies how likely we are to see a particular output given the state the model is in. For instance, at the bottom, we see that if the weather is rainy today, there's a 60% chance that Bob will be grumpy. Finally, we have the transition probability, which specifies how likely we are to transition from one state to another state. In every time step, the model can transition between different states. So for instance, at the top, we see that if the weather is sunny today, there's a 75% chance that it will be sunny again tomorrow. All right, so now we know how an HMM works. Let's look at how sparsity comes into play here. So let's assume we have this model, and we have some sequence of outputs that we've seen. So we have seen Bob's mood be happy on one day, and then 3 days after that, he was grumpy. And we can illustrate the possible states that our model can take during these time steps with a sort of graph, which is called a trellis, which also happens to be where we got the name from. So in this graph, we start from the start node on the left-hand side, and then we can choose whether to go to the sunny or rainy state in every time step. So it sort of illustrates the possible paths that we could take, the possible states that the model could have been through during these time steps. And then each path ends in S4 or R4 because that's our final observation. Now, if we look at one of the algorithms that we implement in Trellis, and which is an interesting application of HMMs, is the Viterbi algorithm, or decoding algorithm, where we look for the most likely sequence of states. So in terms of the trellis, we're looking for the path from the start node to S4 or R4 for which the probability is the highest. And we can compute that because we have the model with all the probabilities we need and the output sequence. So what that means in this example is that Alice can, just using this model and looking at Bob's mood over a series of days, she can determine the most likely weather in his city. And at least I think that's pretty cool. But of course, where does sparsity come into play here? So let's assume that the probability of the rainy state transitioning back to the rainy state was 0, so we couldn't have rain 2 days in a row. In this case, there's some sparsity because we know that we can ignore those paths where we pass through 2 rainy states in a row in the trellis. And this is where sparsity, this is like why sparsity is important, because this allows us to reduce the number of paths that we need to consider for the Viterbi algorithm. And in this case, we just have 2 states, so it's not that important. But if, imagine we had hundreds or thousands of states and lots of transitions with probability 0, well, in that case, we would save a lot by considering the sparsity. And that's what previous work doesn't really allow you to do. So let's move over to the language. So Trellis, as I said, is a declarative language for describing HMMs. And now I'm going to show you an example of a sparse model in Trellis. This is, I don't expect you to read the code, by the way. I'm going to go through the main parts. But this model is 27 lines of code, and we implemented it from a CUDA implementation of many hundreds of lines of code. And it is used to, it can be used to decode a nucleotide sequence from some abstract signal values. So let's go through the main part. At the top, we have some high-level declarations. So, because we can reason about the type of a state and an output in the model on a high level, so we don't have to think of it as integers, even though in the end, that's what we're working with for performance. But the compiler handles that translation for us. Then we have some tables which declare the data that the user has to provide at runtime. So this is something that's provided outside of Trellis, sort of, when the user uses the generated code. Then we have the initial and output probabilities, and these are just defined in terms of these tables. And at the bottom, we have the transition probability, and this is the interesting part, because here is where we want to make use of the sparsity we have in our transitions. So the way we do it is that we have different cases, and each case describes how we compute the probability for a set of transitions. And if we don't have a set for which a transition belongs in, then we know that its probability is 0. So we don't have to say anything about the states that are, or the transitions that are impossible. So let's look at an example of this. So in this case, we have, so on the left-hand side, we have a set constraint, which describes pairs of states. And it consists of a predecessor state that we're transitioning from, and a target state that we're transitioning to, and then we have some constraints on these states. So this set describes the possible transitions for which we define how to compute the probability. And so on the right-hand side, we have an expression body which determines how we actually compute the probability. And in this case, it's just a literal, but we could also refer to the tables that we declare in the model. Let's move over to the compiler. So now I'm just going to give an overview of the compiler, and then we'll dive into the sparsity part. So the compiler starts from the left-hand side with a model, like the one I showed you earlier. Then we parse it to get an AST. So by the way, the blue boxes are compiler passes. And I'm omitting the intermediate artifacts for brevity. So the Trellis model compiler lowers down like high-level abstractions, such as the type of a state, because we can reason about it as a tuple of multiple abstract types, but this lowers it down to integers for efficiency reasons. Then we have the set constraint validator, where we validate certain properties on the set constraints. For instance, when we have multiple cases in the transition probability function, we want them to be disjoint because this allows us to generate much more efficient code because we don't have to do any bookkeeping of which predecessors we've seen so far. And we do this using the Z3 prover. Then we run the predecessor analyzer where we compute the predecessors, and this is the key part of making use of sparsity in the models. And this is what I'll talk about on the next slide. But then we have the CUDA compiler. So there we translate the Trellis AST that we have built up so far to CUDA C++, and then we compile that to a shared library. We also use a Python builder to generate a Python library, which uses this shared library to sort of perform calls to the GPU code. So what this means in the end is that the user can write a Trellis model and they don't have to write a single line of GPU code themselves, but they still get the ability to make use of efficient GPU code. So let's move over to the predecessor calculation. So what we want is we have some target state, like up on the right-hand side, and we want to find which states we could have come from, so which states have a non-zero probability of transitioning to this state. The problem is that brute forcing this takes quadratic time in the number of states because we have to consider every possible predecessor in the general case if we don't do something clever. So we use two different approaches in Trellis. The first is a compile time approach where we brute force at compile time. So we only pay this cost once, and then at runtime we look it up in arrays so that we sort of eliminate that overhead of having to do it in every time step, which would be, yeah, it wouldn't be beneficial. And the nice thing about this is that it's super general. It works for any Trellis model. The problem, though, turns out to be that it leads to a very high memory bandwidth use, which is bad on a GPU. And because of this, we also implement a runtime approach where we perform an analysis at compile time to figure out which predecessors, or we figure out a way to compute the predecessors so that we can compute them efficiently at runtime. And this approach has the drawback that it doesn't work for any Trellis model because we make assumptions on how the set constraints are defined. But let's look at that, because I think the brute force part is kind of clear. But if we want to compute the predecessors at runtime, how do we actually do that? Well, if we consider this case where we have a state is a triple, and each element of the triple is an integer value, 1, 2, or 3. Then if we start from the target state, DEF, we want to find an expression for computing the predecessors. So what we do is we just go through the constraints one by one and building up this constraint. So first we see that C must be equal to D. So the third component of the target state must be D. Then we have that the second component of the target state must be 1. And this means that if we had a target state of 1, 2, 3, then we know that we cannot have a predecessor from this case. So we can immediately exclude them with a simple if statement. Finally, we have the constraint that A must be equal to F, meaning that the first component of the predecessor must be equal to whatever F is. So for any fixed state DEF, where E is 1, we can find 3 predecessors because we don't have any constraints on the second component. So we can generate them by looping over the possible values. So let's look at some of the results. First, I want to point out about the compilation times of Trellis. So it's really fast. It takes less than 7 seconds for all the benchmarks we had. And this includes a case where we run the predecessor pre-computing the predecessors at compile time with the quadratic time approach on a model with more than 200,000 states. So, and it also includes the time needed to compile the CUDA code. So compilation times are very fast. And I just want to mention this because previous work doesn't need to be compiled. So in the first graph that I want to look at, we compare the performance between Trellis and Zip HMM and Palmkvist running on both CPU and GPU. And for Trellis, we evaluate 2 different versions because we can either compile the same model using the compile time approach or the runtime approach for computing predecessors. This is for a sparse model, of course. And we see that Trellis is significantly faster than all the other models. And even if we had included the compilation times, Trellis would still be much faster than the others. The second part I would like to talk about is the graph at the bottom, where we have compared Trellis against a native CUDA implementation that was written before we even started working on Trellis. And in this case, we have 3 different versions of the sparse model. So k equal to 3, 5, and 7 represent like the number of states, essentially. So the 7, when k is equal to 7, for instance, we have 260,000 states, roughly. And in this case, the first thing we see is that the runtime approach of Trellis, so Trellis RT, is able to match the performance of this native CUDA code. And this means that we can write our models in this high-level language and still get code in the end that is as efficient as if we had written hand-optimized CUDA code for this particular model. But of course, the benefit is that we can then move over to, we can change the model much more easily in Trellis than in the CUDA implementation, of course. The second takeaway is something that I mentioned earlier, that the runtime approach is significantly faster than the compile time approach. And this is because, as I said, the high bandwidth use of the compile time approach, where we constantly do lookups in arrays, really slows down the GPU because it's a bottleneck. So by moving some of the workload to the compute units of the GPU, we can improve performance quite drastically. Okay. So to conclude, Trellis is a domain-specific language designed specifically for sparse HMMs. And as we saw in the previous slides, it is able to significantly outperform previous work for sparse HMMs. And it's also able to match the performance of a handwritten CUDA kernel. Thank you for listening.
Yes, thank you very much. Are there questions? Okay, maybe to kick off questions.
Yeah.
Well, you said that you're explicitly good at using dense HMMs. Sorry, sparse.
Sparse.
Now I want to turn the table around.
Yeah.
What about dense? Can you do them as well? And how do you compare to other tools?
So we can do dense as well. I mean, it's much easier to express them because you could express it in Trellis by just having one case matching all the possible transitions and then just look up in a table. It's not optimized for that case, but we do evaluate that as well in the paper, and we do quite well. So, I mean, we're not far off the others.
Yeah, thanks for the talk. In your slides, you said you are translating it to Python.
Yeah, we generate like a Python wrapper, which calls the generated GPU code.
Yeah, so I was just wondering, why did you consider generating Python wrapper code, not directly CUDA code?
I mean, it's convenience, because it's much more convenient to work in Python, I think, at least, and I think users would prefer it.
The follow-up question would be, do you think if you had generated the CUDA code directly, you could have done anything better?
I mean, I have the CUDA code. We could just call the CUDA code directly. It's just that we choose to like call it from a Python wrapper. So I mean, we have the generated CUDA code, so we could call it directly from C++.
Right.
As well.
Right. I was just wondering if that would have been more. I mean,
yeah,
calling from C++ or CUDA directly would have been. Would it have been more efficient?
Yeah, it probably would be more efficient, slightly. Like I didn't say that, but like we showed, the blue bar shows like the time including overheads. So, and the red is just the actual algorithm. So yeah, there is a bit of overhead that we could eliminate by doing that.
Further questions? Okay, then maybe one last question from my side. When you presented your backtracking approach, who does actually specify the constraints? Are they directly within the Markov model, within your model, or how do they come into place during your pipeline?
So the constraints are specified in the language. So like if we go here, so like at the bottom there, you see the 4 different constraints and the
okay, so you derive them directly from the transitions, which are
so they're part of the model. They kind of encode the structure of the sparsity in your model.
Okay, let's thank the speaker again.